So far we have discussed a large number of feedback systems, including that of universal active filter and then the self-tuned filter. Today we will be discussing about an important analog block that is currently being used, that is phase lock loop or PLL. Strictly speaking, a frequency lock loop. We'll see that phase lock loop is, in a strict sense, is valid for the self-tuned filter, where we were able to lock the phase of the system to pi by 2, and that happens when the incoming frequency and the frequency of the filter pole are the same. So today I'll elaborate more about feedback systems. Now this is a conventional feedback system in controls, which has been taught to almost everybody. We have any variable xi at the input, okay, and an error detector senses the output variable x0, okay, as xi minus x0. That error detector output is amplified by an amplifier G, okay, so that the loop gain is increased enormously. Then x0 output is equal to G times the error xi minus x0. Then x0 by xi is always equal to G by 1 plus G, or it is approximately equal to 1 if G is made very large compared to 1. This is the basic principle of negative feedback system. Here we have the loop gain becoming negative because G is the gain here and there is an inversion here. So as long as the loop gain is negative, it is a negative feedback system, this thing happens. And if xi and x0 are just voltages and the error detector is a difference in voltage or a differential amplifier, then this is a voltage amplification factor, difference gain, then automatically it becomes a voltage follower. If xi is current input and x0 is output current, and that can be detected, error can be detected at a single node, okay, instead of the voltage error at 2 nodes, okay, it can be detected at a single node, and that error current is amplified by a current amplifier with gain equal to G, current gain equal to G, then it becomes a current follower. If on the other hand phi I and phi naught are the phase differences of the signal, sinusoidal signal, then this error detector is nothing but a phase detector, which is a multiplier. That also we have seen in the last class, how a multiplier can be used as a phase detector, and then that passing through a low pass filter and an amplifier increases the loop gain, and that voltage is converted back to phase by using what is called a voltage controlled phase generator, which is nothing but a filter that is getting tuned by a voltage. Okay, that we had seen in the earlier experiment. So that is called a phase follower, okay, which is a true phase lock loop. Next we can have omega I, xi as omega I, frequency, and x0 as frequency. Actually the phase detector measures only the total phase difference. So phase and frequency are linearly related, and therefore the error detector won't know if the frequencies are coming as input or phase get to the input, okay. So it will just measure the phase difference, okay, even when the frequencies are different. And then again the low pass filter will take the average of the output, okay, and that voltage is converted back to frequency by using a VCO, which we have already built in the FM generator experiment, right? So we know all the blocks, and therefore now this block is nothing but the frequency lock loop, or what is conventionally called as phase lock loop, okay. So here we have to start with analyzing this, assuming that this is phi I and this is phi naught, and this gives you an output corresponding to kPd into phi I minus phi naught. So it is an average voltage corresponding to the sensitivity factor of the phase detector, which is nothing but delta phi divided by that is delta V average divided by delta phi. It's nothing but kPd, sensitivity factor. Okay, and then that average is taken by the low pass filter and amplified by A0 and applied to the VCO input, and the VCO converts it into frequency, and kVCO is nothing but delta omega divided by delta VCO. And that also we have defined in the earlier experiment. So how to find out kVCO? It is nothing but the change in frequency corresponding to a change in voltage at the input of the VCO. And this parameter kVCO is giving the output as frequency. However, the phase detector senses it as phase error. That means the relationship between phase and the frequency is 1 over S. So the transfer function of the VCO can be interpreted as, when it is detecting phase at the output, as kVCO by S. Okay, because d phi by dt is omega. So S into phi is equal to omega S. Okay, so phi is omega by S. So that is why this transfer function becomes kVCO by S. So the overall loop gain is going to be kPd, okay, into phi I minus phi naught, okay, into A0 by 1 plus S by omega LP, assuming that the low pass filter is averaging it this way. And then we have the VCO sensitivity coming into picture, kVCO. So it has got converted to frequency. Now that divided by S reconverts it into phase, and that is equal to phi naught. So we get, okay, delta phi naught by delta phi I, again as loop gain. This is GL divided by 1 plus GL, where GL is, okay, kPd kVCO into A0 divided by S, 1 plus S by omega. Because of this S, right, the dimension of GL, okay, is also going to be frequency. That GL naught, this factor, GL naught, is going to be also frequency. So the frequency by frequency is a loop gain. Right? So this is an important thing, and therefore if you now find out delta phi naught by delta phi I, this is going to be 1 by 1 plus 1 over GL, right? So this becomes nothing but S by GL naught. That's S squared by GL naught. So this is the second order system, like we did in the case of filter. This is omega naught, natural frequency of the system equal to root of GL naught into omega L. That is the natural frequency of the phase locked loop system. And again we can write this as 1 over 1 plus S by omega naught cube, S squared by omega naught square. Omega naught is the natural frequency, then Q becomes equal to root of GL naught. That means as a phase follower, this frequency follower behaves this way, that delta phi naught by delta phi I is equal to 1 by this, okay, or it is going to be also unity only for low frequency ranges, and it will be following the incoming phase only if the rate of change of phase is low. Okay, if the rate of change of phase is very high, then it starts speaking like this. Okay, and therefore this is going to be Q. This is unity. This is the magnitude function varying with respect to frequency. This is around the natural frequency omega. So we must work at a rate such that the rate of change of phase is pretty low in its frequency compared to the natural frequency of the system. Then only it acts as a phase follower. So we have just seen how a phase following action occurs when we are using a VCO in one of the loops with phase detector as the error detector and amplifier plus low pass filter to boost up the loop gain of the system. Now a phase follower is nothing but a frequency follower, because at the same time, if you consider delta phi naught by delta t by delta phi I by delta t is also equal to 1 in this, right, if this is satisfied. What does this mean? This is nothing but omega naught output frequency, and this is nothing but input frequency. So output frequency becomes the same as input frequency, and we have now established that output frequency follows the input frequency. If this input frequency is an FM, you get an FM here, right? An FM is produced by VCO that we had seen, right, by applying a modulating signal at this point. So this FM produces the same FM here, right? And that means this is a VCO. This reproduces this. So this can be used for detecting an FM or FSK. So the phase lock loop is one of the important applications, is to detect the FM, okay, when the line contains large number of such FM, okay, at different carrier frequencies. It selects the FM, okay, from the lot of FMs coming in the channel. That selection procedure we can understand if you understand how, when initially we have a incoming frequency which is the same as what is called free running frequency. This particular VCO, even when nothing is applied here, okay, is at some VCQ, let us see, corresponding to which this is running at a quiescent frequency of omega naught q. So then if omega I is equal to omega naught q, which is the same as the output frequency of the VCO prior to application of any input, then also nothing should happen, because this frequency is same as the incoming frequency. If nothing should happen, nothing should change here. If nothing should change here, nothing should change here, right? Which means the output here, which corresponds to cos phi, if we have seen when this is used as a multiplier, this output average corresponds to cos phi. So cos phi has to be 0, or phi automatically, the phase difference gets adjusted to 90 degrees, pi by 2. This is an important thing. When the incoming frequency is same as free running frequency, the phase difference gets adjusted to pi by 2. This you can observe in the actual system when you build this. Please test it out. Then when you change omega I away from omega naught q, this output should change correspondingly to make this equal to the new omega I. That means this output will change by omega I minus omega naught q divided by k VCO, assuming that it is a linear VCO, right? So that is the DC change, and that DC change divided by A naught is the voltage change here. So this can go on until the phase change can no more get followed, because the sensitivity here keeps on decreasing because it's a cos phi. So when it is changing from pi by 2, the phase change here, which is the result of some average, is going to be cos phi equal to that finite DC value, right? So that will keep on changing until it reaches a maximum, right, on one side and another minimum on the other side. And therefore this particular limit is called the lock range, beyond which it is not capable of getting locked to the incoming frequency. So please test this out. See whether your phase lock loop is getting locked onto the incoming frequency. Beyond this range, it suddenly comes back to the pre-running frequency. So the aim of the experiment is to understand phase locking or frequency locking.